Okay, so our next paper is entitled Multimodal Journey Planning in the Presence of Uncertainty. It is by Adi Botea, F. Dokia Nikolova, and Michelle Berlingerio, and it's going to be presented by Adi.
Thank you, Blai. Yes, this is a joint work with Evdokia and Michele. And this is about multimodal journey transportation. I presume most people in the room know what that problem is, but just to be on the same page. Here we talk about combining into the same trip several transportation modes in a city. For example, somebody can catch a bus, ride the bus for a while, then get off, walk to a bicycle station, rent a bicycle, cycle, park the bicycle station, and so on and so forth. Everything into the same trip. Why do we care about this problem? Well, it's getting fairly popular recently for a number of reasons. One of the reasons being that there is some practical interest behind it and even some commercial interest. And in addition to that, there is more and more data available. Some of that data is static, such as the timetables of buses, for example. But part of the data is also about real-time updates about, for example, the estimated times of arrivals of buses at stops. And there are more reasons. Even the availability of mobile phones helps, because with that we can think about how to track a user along the journey and how to trigger replanning in a smart way when that is necessary. We assume that there is uncertainty about this problem, and the truth is that there is uncertainty in our understanding of a transportation network in real life. That uncertainty can stem from various places. For example, we don't really know the exact arrival time of a bus at a stop, but we can estimate that, and we can also estimate the uncertainty around that, and so on, right? We don't know for a fact whether an accident will happen, the exact duration of the rush hour, and so on and so forth. And in this domain, even small inaccuracies in our knowledge about the network can actually have quite a big impact on the solutions that we compute. Because here, journeys can actually be a sum of multiple legs, right? If we change modes, then we drop from one bus and catch another, for example. And if we miss one connection by only 1 minute, that can be very bad already, because we can arrive at the destination much later than we planned. So the effect can be 1 hour delay, 2 hours delay, and so on, even just because of a small delay somewhere in the middle of the trip. So this is why we look at the uncertainty. And next I'm going to introduce the domain in the way we represent it and we handle it. So this almost looks like classical planning, in the sense that we have some sort of an input file which looks like the domain file, the one up there, and also something that looks like the instance file. So the one at the top is called the multimodal network snapshot. That includes all the information that we need about the transportation network. For example, we need data about the scheduled public transport, such as buses, because we are going to handle that. We handle bicycles, so we need data about shared bicycles in a city. And optionally, one can have more in there. If you want to have private cars in the picture, then put the relevant information in there. The file at the bottom is actually the plan request submitted by a user, and it contains the obvious information, the origin of the trip, the destination, the starting time, also the modes allowed, right? Some users will say, it's fine to ride a bus, but I don't want to cycle. So those are the modes. And also what I call the maximal quotas. Some users will say, I'm willing to walk for at most 20 minutes. So that is the maximum walking time quota. Right, the maximum number of interchanges is another quota considered, and also the maximum cycling time. And optionally, one can add more in there. All right, a closer look at the snapshot data. So that was the file at the top. As I hinted earlier, here we handle scheduled public transport data and also bicycles. So about the scheduled transport data, we need to know the stops. And the data about a stop includes the latitude, the longitude, the name, the ID of that place. We also need to know the routes. And one route is an ordered sequence of stops. We also need to know the trips. One trip is the actual journey of a bus along a route. So in addition to the route itself here, we need to know the time of arrival at a stop and also the time of departure. We represent the time as probability distributions for the very reason that we handle uncertainty here in this work. This has some similarity with the structure of the standard GTFS, but in addition to that, we handle uncertainty and we also handle bicycles. And there are some technical differences which are beyond the purpose of my talk today. In terms of bicycle stations, we need to know the location of the stations, right? So as in the case of stops, we need to know the latitude, the longitude, the name of that bicycle station, that sort of stuff. Our assumption here is that a bicycle will always be available when we need one, and also a parking spot will always be available when we need one. Right, that was my quick introduction of the domain, and the next step would be to build a state space based on that domain, such that later on we can search through it to compute a journey plan. What are states here? A state has a number of, say the basic variables and also some additional auxiliary variables. I will talk in particular about the main ones. The first one is the position, and that represents the position of the user. It can be a ground location, such as the origin or the destination, or a bus stop or a bicycle station, right? Or it can be a trip ID. That's for the case when the user has boarded a trip, and therefore that's the position of the user. The time here is the time when the user arrives at that position. And as we model this as a probability distribution, as I said earlier. We also encode in a state the quotas left. We have some initial quotas at the beginning, being the maximum quotas specified by the user. And as we make progress along a pathway in the search space, we spend some of the quotas, right? We walk for a little bit, we cycle for a little bit. So in every state, we record how much, how much quotas we have left to complete the journey. And then there are some auxiliary variables in the, very, very simple stuff. With the obvious purpose of making things, ensuring the correctness of, applying the right actions in the right states, making sure that preconditions hold and stuff like that. A quick look at the actions now. Action take trip is a non-deterministic action in the sense that it can have up to 2 successors. Those are corresponding to the cases when the action succeeds, therefore we are able to catch the trip, or the action fails, and in that case we miss the bus. Get off trip is modeled as a deterministic action. That means that we have exactly 1 successor state, and that means that we always succeed in getting off a bus when we want to get off that bus. Walk is also deterministic in the sense that there is exactly 1 successor state. We always succeed in completing a walk. But what is uncertain here is the duration of the walk, which is once again modeled as a distribution of a probability. Higher bike is deterministic, it always succeeds. Cycle is very similar to walking, and park bike is deterministic again because we always, under our assumptions, we are always able to park the bike at a station. Now I take a quick look at the non-deterministic action that we have, and my purpose with this slide is to give you a flavor about how our modeling of the time, that is a continuous stochastic time, but in the end we have a discrete and/or state space, and I want to give you a clue here about how that continuous stochastic time impacts the structure of our discrete and/or state space. So we have the action take trip, 2 successors, 1 successful, the other one fails. And we want to compute the probabilities of being able to go along one branch or the other branch. So if U is the random variable modeling the user's arrival time at the stop, and B is the random variable modeling the trip's arrival at the stop, and if these 2 are independent, then we can compute the probability of catching the bus with a formula like that one over there. And now, if these are arbitrary distributions, maybe that can be difficult to compute analytically. But what we can do is to do Monte Carlo sampling to estimate that probability. And also in the particular cases of some distributions, we can maybe resort to the theory to compute estimations of that with a formula. For example, that is the case when the distributions are normal. Okay, so we have built a state space. Now we have to search through it. The approach is contingent planning as heuristic search. Well, as you saw earlier, by contingent planning, I mean contingent planning with probabilities, because we have probabilities there as well. We implemented a weighted AO star, and we searched that in a tree as opposed to doing that in a graph. And also notice that we don't do belief state aggregation. So the states are represented explicitly, and we search directly into that space. We have built an admissible heuristic, and also we came up with some pruning rules based on state dominance. As optimality criteria, now the framework here is that we have a contingent plan with one or more branches, right? Because we do contingent planning. And the main optimality criterion refers to minimizing the worst case arrival time across all the branches on the tree. That means we want to play it safe, right? We want to give some guarantee about the arrival time in the worst case. The tie breaking is performed by minimizing the expected arrival time. That is the weighted sum of all the arrival times along all the branches. Right, how do we compute the heuristic? Well, ideas similar to what we do here have been used in the past, but just for the, to have an understanding, I'm going to go quickly over it because, the exact details might be different. So the heuristic is computed as a lookup table, and what we compute there is an estimation of the travel time from every ground location to the destination. To be able to build that, first we build a relaxed graph. As nodes, we put all the ground locations, right? The origin, the destination, the bicycle station, and all the bicycle stations and all the stops are nodes. And then we start adding the edges. We add an edge between any two consecutive stops along a route. If two nodes are within walking distance from each other, we add an edge. If two bicycle stations are within cycling distance from each other, we add an edge. And that's how we build a graph. Notice that this is a relaxed graph because we ignore a number of details here. For example, we assume we never have to wait, we assume we never miss a trip, and we assume there is never a slowdown along any link in this graph. So that gives us admissible estimates, and of course, the last step is to run Dijkstra backwards from the destination to compute the lookup table. Pruning with state dominance. So this is the definition of state dominance that we use. And unlike other work that we have seen today, I use the relation the other way around. So here the better state is the one at the left. Right? To be able to compare two states with state dominance, we require that they talk about the same location, the same position of the user, and then one state has to be better than the other in terms of the resources, right? By resources, here I mean the quotas left, and also the arrival time of the user. So if the user arrives earlier, then that's better. And that is the definition of the time. Dominance is a little bit too strong, but this is what we used in this work anyways. And we have a theoretical result that tells us when it is safe to prune with state dominance in our state space. And notice that here we talk about looking for optimal plans. As we will see later in the experiments, this is quite an important keyword, actually. And the idea is very simple, really. So, can I point with this? I don't know. Right? So S1 is a deterministic successor of a state S, and S2 is a descendant of the same state S on a path which contains no failed branches. So all the branches on that path can be either successful branches or deterministic branches. And in that case, if S1 dominates S2, then we can prune away S2 by assigning a cost of infinity to it. Now I change gears a little bit and present very briefly a harness result that we have. The context is slightly different, and I have to clarify the context first. So what we have here is a standard graph with nodes and edges. By standard, I mean there is no and/or structure considered here. And then the costs of the edges are random variables, but the distributions of these variables are not static all the time, right? They stay fixed for a while, and at some point they change into something else. As an intuitive example, think about the rush hour and also the off-peak traffic. So the distributions can be different in these two cases. And the theorem says that it is NP hard to compute the worst case cost along a given path. The idea of the proof is to reduce from the subset sum problem. Moving on and talking about the experiments. We used data from Dublin, and in Dublin, buses report their GPS position every 20 seconds. So we had 1 month of GPS records for the working days of the week. We analyzed those GPS records to compute expected arrival times of buses at stops and also the standard deviation around those average values. On top of that, we assumed that the distributions of bus arrival times are normal, and then we cut that to the 99.7 coverage range. When we had to compute the probabilities as indicated earlier, then we do Monte Carlo sampling, and we sample 500 times from each of the variables that are involved. You see a few other numbers here. It's more than 3,600 locations, right, including about 3,500 bus stops, 44 bike stations, and a few points of interest, more than 200 routes, and 3,700 trips per day. This is a summary of the anytime behavior of weighted AO star. The news is good, and this is maybe not too surprising because similarly good behavior has been observed about weighted search, weighted A star, or even weighted AO star in other domains. But so why is this good news? Because you can see that with bigger weights, the suboptimality is not too bad, but the speed up is quite good actually. And this, among other things, indicates that the heuristic is somewhat informative, right? If the heuristic was useless, then we could give it any weight and it probably wouldn't work too well. This is a chart about pruning on and off. And if the dots are beyond the diagonal, that means that pruning helps. As expected, it works for a weight of 1, because weight 1 means optimal search. Interestingly, we also obtain savings when the weight is 2. But for larger weights, we start to see very mixed behavior, and that is not entirely surprising, because remember, the theory refers only to optimal planning and doesn't tell you much about suboptimal. In fact, you can explain why you see a mixed behavior when the weights are so big. So in summary, we looked at multimodal journey planning under uncertainty. We showed an NP hardness result when the cost, when the distributions of the costs change in time. Then the approach that we took is based on contingent planning as weighted best first search. And to us, the results showed that the approach is viable, but they also show lots of room for improvement. And in fact, we kept working on this in the recent month. What we did, we improved the heuristic, and the idea was very simple. The computation I mentioned earlier takes the full timetable for the full day. But if we restrict that to a relevant time window, we end up with more accurate estimations because we ignore things outside the window, which is irrelevant anyways. Stronger pruning with dominance, we managed to extend that definition of dominance, and we got better results now. We also have an additional type of pruning, which uses admissible estimates of the quotas left. So in a given state, we look at the quotas we spent so far, We add that to the admissible estimate of the quotas needed to achieve the destination, and if that is greater than the maximum quota allowed by the user, then we can prune. That is quite effective in some cases. And processing per stage has been improved, and it's a lot faster now, and we consider more cost metrics, such as linear combinations of time and the number of legs in a journey, both being quite relevant in practice, I think. In the future, we plan to connect to real-time updates on estimated times of arrival. IBM has the machinery to collect all that data and to give fresh updates on the estimations. And we also look at scalable journey monitoring and replanning. So that refers to traveler tracking pretty much. And that's the end of my talk. Thank you.